The problem that we'll solve as an example here is a good introductory problem. Not a huge amount going on, just a rock that's thrown straight upward with a velocity of 21 meters per second. We would like to find how long the rock is in the air and also to find what the highest point the rock reaches is. We're going to assume the air resistance is negligible, and so there's not a huge amount unusual going on, just a couple things to find. To organize our information, the initial velocity was 21 meters per second. A little bit of hidden information is the acceleration we know is going to be negative g, because we know that the rock is in free fall. Nothing is interacting with it except for gravity. Air resistance is negligible. So we'll be able to say that a is equal to negative g. And then we were saying we wanted to find how long the rock is in the air. I'll call that delta t to give it a symbol. And the highest point the rock reaches, I'll call that delta y, which will just be our change in y position. From the ground upward, that'll be the highest point that's reached. So we'll start by drawing a graph, velocity versus time graph specifically. It might be helpful to know that typical graphs for objects in free fall, when we're talking about vertical motion for velocity, then we know that they're just going to exhibit a straight line downward. Our rock is starting at a point that's positive, where this is going to be 21. I'll call that VI. Once we get our starting point, we know we just need a slanted line straight downward, however far the rock is traveling. It'll just continue on that straight line path. This is kind of an interesting graph to investigate. We know that the line really is a straight line because once the rock stops, which it does in the middle here, in the middle of this graph, we know that it's going to start coming back down and it'll start speeding up again. But this time, the velocity will be negative because the rock will be moving downward. So as we move to larger and larger speed values, we actually want to do that on the bottom half of the graph where everything is negative. And so it turns out that everything is exactly symmetrical in this graph and exactly as a straight line down. And again, knowing certain patterns like this can help you draw out the details a lot more quickly than otherwise maybe could be done. Other things that we can notice in this graph, we would have a total amount of time the rock is in the air will be the full range, delta t. But I feel like it's going to be nice to segment this problem into two pieces. The fact that we have like a triangle above the axis and another triangle below the axis means this problem is going to be very natural to cut into two parts. So why don't we call this part delta t1, just the time for this first segment, this top triangle that's isolated there. And then the position will be the area under the curve. We'll call this delta y. That's how high the rock travels during this first segment of time. Everything after this will be then falling back down and would not be relevant for the highest point. So I can label delta y right here. It'll also be useful to have an acceleration graph. We said that the acceleration is going to be given by g. I'll label that here. The acceleration on the side here, I will just label this side as g. Now I know that the acceleration is actually negative g, but the way that I usually like to account for negative signs in these kinds of problems is just to treat everything possible as just a magnitude. I know that the magnitude of the acceleration is just g. Now I took account of the negative sign by making sure that I drew that line below the axis. On my acceleration graph, I want to make sure that the acceleration is below the axis in the negative side of the graph. But once I actually start to label the sides of these geometrical shapes, I'm just going to focus on that the side length of that rectangle is just g. Yes, it is negative being below the axis, but I don't need to write the negative here. I'm more concerned just with the area of this rectangle, and the side length of that rectangle geometrically is just a positive g. The negative sign has already been taken into consideration. We know that the area in the acceleration graph would be the change in velocity. I'm going to go ahead and only draw this graph for the first segment that I'm focusing in on. So I'm going to label this as delta t1. Of course, the rest of the motion coming back down would look exactly the same. But in order to focus in on that first triangle on my velocity graph, I'll go ahead and just focus in on that same segment in my acceleration graph. And I'll draw the rest of it if need be. So I'll go ahead and label delta t1 and then delta v1 to make sure that I know that this delta v is only for that first segment. So if I were to go and try to label delta v1 on my velocity graph, I would find that by just saying that the initial point is up here at the start, and the final point in the segment would just be this point in the middle of the graph. The final point overall would be farther along, but we're just focusing on that first triangle. So with these two dots, we have the initial and the final points of the motion. Well, on the velocity axis, we would have a hash mark here and here to label those 2 points, and therefore between those final and initial values, this would be our delta v1. What we can see based on that discussion is that delta v1 and vi are exactly the same value. So we can identify those with each other. All right, so it looks like everything important for the moment has been labeled. So let's go ahead and try to start working out what we are interested in finding. We're interested in finding delta t. And the first thing I think I'll do is just draw out the equation for this rectangle in the acceleration graph. So the area delta v1 would be given by just the length and width of the rectangle. That's going to be g and delta t1 like this. I'm going to remember, based on what we just noticed, that delta v1 is the same as vi, and vi is known, so I'll go ahead and rewrite this equation using vi. And then now I can start to look at this equation in more detail, try to look at it strategically, and say that the delta t is what I'm really interested in finding, but the g and the vi, those are both known. And that means that I could go ahead and solve this right away. I don't need to do any further work. Even though I have equations I could write on the velocity graph, I actually don't need that, at least for this first question that I'm trying to find the answer to. So if I solve algebraically for delta t1, I would divide g to the other side. Once I've solved it algebraically, I'll go ahead and plug in the numbers for this. Vi is 21 meters per second. G is 9.8. I'm plugging in numbers here. I get 2.143. Now I was really interested in the total time, not just the time during the upward segment, but I can rely on symmetry at this point of the problem. It would also be allowable to go ahead and proceed to analyze the second segment of the motion, this triangle below the axis. But I should take a shortcut if I can, if I notice it, and know that the return motion back down is going to be exactly symmetrical with the motion going up. So the full delta t would just be double the delta t1 that we solved for. Plugging in the numbers here, we'll have 4.286, which rounding would be 4.3 seconds. So this is the answer to our first question that we were trying to figure out. In order to find the answer to the second segment, we're now going to focus our attention on delta y. We find delta y as the area inside of the triangle that we've been focusing on, and the area of a triangle is half base times height. So I could use vi and delta t1 for those. That would be sufficient. All of these at this point are known. We worked out delta t1 just to the side, and vi was given in the problem. So plugging in numbers for this, I find that the full height would be 22.5 meters. I've been working in SI units throughout this problem, so I know that the final answer will be in meters. And so this wraps up the problem.